Good morning. For those of you who missed the subnetting lesson, in this video I want to take you through how we do subnetting. And when you look at the bigger picture, we are now at layer 3. Remember, in the previous lesson we looked at the transport layer, and here is like where we are going. I said that CCNA1 is like they have inverted the OSI model. So we are at layer 3, which you can see is a huge topic in CCNA1. It is covered in 3 topics all about IP addressing. And so we said that the transport layer, and mainly here we talked about TCP and UDP stuff. So, but I also said that another huge thing that is defined at the transport layer is port numbers. So port numbers would be, is what I said here. I'm trying to draw your laptop here. So when you connect to the network, going to some server, could be the Facebook. So let's say this is Google server. We said that the port numbers are analogous to the name, on the envelope, yeah? Because we said computers, the communication that computers do on our networks can be analogous to the good old postal mail system where you have, so you know that on the envelope you write your name or the name of the receiver, then the PO box and all that stuff. So I said the OSI model basically is like the enveloping standard that computers use, so that the packets that are being sent between your computer to Google's website, so that you can receive that website, they sort of, as in they follow that standard. So I say that the port numbers are analogous to the name. The PO box would be analogous to the IP addresses, because it's the IP addresses that identify the server. Remember that the internet is a gigantic web of routers, yeah, interconnected everywhere, and you have so many, we all know the internet, you have so many servers around. So this server will have a specific IP address here, or a unique IP address. That's the term I was searching. And this one will be unique. So it's the IP addresses that identify the server. Now it's the port numbers that identify the service. Yeah. So the service here, if we come back to this analogy, would be like now, say if I send a letter to Baraton, I'll use maybe a common PO box, which is a common IP address that, a common PO box, but is the name that will identify the person that I want to communicate to. So likewise, so on this server, it could be having a lot of services running on it. It can be a mail server. We all know that Google is a huge data center, whatever, yeah, cloud computing, and also this could be a mail server, could be a telnet server. All is a lot of services, yeah. So anyway, I think I have belabored on what we talked about in the previous lesson. So now here, for us to, so as you can see the title, IP version 4 address format. So we need to understand the IP addresses, the PO box in greater details. So I think you have all seen IP addresses. They come in this format. There's an example, as in it's a four decimal number separated with periods or dots, and every field can range from 0 to 255. That's what I have here. So the least IP address you can have is 0.0.0.0, and the highest you can have is that, yeah. And so we cannot assign this to a machine, and this we cannot assign it. So I think we know the format of IP addresses. Now An IP address is always combined with a subnet mask and typically combined with a default gateway. Yeah. So the reason why an IP address is always combined with a subnet mask is because whereas as we see an IP address as 4 fields, where you have this, or 4 groups of decimal number, your computer sees them as, you know that a computer is a binary machine, so it sees them as ones and zeros, yeah? So what I've written here is, this would be, say, a typical IP address, is what actually we have here in this slide. These 2 IP addresses. So I was saying that your computer will see them in binary, like what we have here. So if you convert 10 to binary, you can use your calculator for now, because we have not looked at how you convert them, but we will in the next slides. So you'll see that 10, if you just go to the calc, where is mine? Calc, if you say come in decimal 10, you can see in binary is 1010. But because it's an 8-bit field, we put leading zeros here. So 4 zeros, because we are working with 8 bits. Yeah. So these IP addresses are actually, as we see them as 4 groups of number, but it's in computers see them as 8 groups of binary digits or bits. Yeah. So what a computer does is, before it can communicate over the network, it will need to know in which network am I in. So this computer will know that I belong in the network of 10.1.1.0, and it does that using what we call AND, a simple ANDing process. So basically what that is, if I can draw, let me take a straight line so that I need to come back, pick my pen. So ANDing is simply multiplication. So we have 0 times 1, of course, is 0. So we'll have 4 zeros, right? Then we have 10, 10. So all these are zeros, 1, as in here we have a dot, because, yeah, dot. So all this will be 0. So you have 1, 2, 3, 4, 5, 6, 7. The last one, 1 times 1, of course, is 1. A dot, the same thing, 1, 2, 3, 4, 5, 6, 7, 8. This other thing will all be zeros, because this whole thing doesn't matter if you're multiplying with zeros. So you have 1, 2, 3, 4, 5, 6, 7, 8. So if you convert this thing back to decimal, you'll have that. So this computer knows that I'm of the network 10.1.1.0. So when it is communicating to, if you remember the tail of the 2 IP packets that we talked about. So when this computer is communicating with this guy, when it is doing its ARP, address resolution protocol, to get the MAC address of the receiver, because he is the sender, he is the receiver. To get that MAC address, it will ARP for it directly. Yeah. But if, say, we were pinging from this computer A to the server here, by a simple ANDing process, it knows that I'm of the network 10.1.1.0. He is of 10.5. Hold it right there. We are not in the same network. So this computer knows that if I send an ARP is a broadcast packet, so even if I send it the whole day, there's no way I can reach them, because we are not in the same network. So this computer knows that I need to go through the default gateway. So it will ARP for the MAC address of this interface of the router. Yeah. so that it can send those packets to the router. The router then will do the routing, and it will be able to forward that packet to the correct destination. So that's why we say that it is always combined with the subnet mask, but typically combined with the default gateway. That is if you are to communicate outside your LAN. So now IP addresses, you see, we have said that the least that you can have is 0.0.0.0. Then you have the highest is all 255s. So one might think that, you see, now that internet started from the US, you expect maybe 0.0.0.1 is assigned to some computer, the oldest computer that came online, yeah? So then you go assigning like that. But that one now would say that the whole world is one big network, one big broadcast domain. So you can imagine, as in, actually that's not practical. So the powers that be, or the people, that is IETF, yeah, Internet Engineering Task Force, came up with rules to manage these IP addresses. First of all, they are limited in that the highest, now that we have seen that an IP address is a 4-group number, but in reality is 4 octets, yeah? What we have here. So in technical terms, you know that these are what we call octets, yeah? It's 4 octets. So if you count the number of bits here, you see you have 8888. So they are all 32. So the highest, the total number of IP addresses in the world, or that you can use, is 2 to power 32, which will give you some 4.7 billion something addresses. Now, the world as of 2018, you have a lot of gadgets that need IP address, or appetite for IP addresses, of course, is far much than the 4.7 billion addresses. I mean, we have smartphones, you have cars that nowadays need or are IP aware, yeah? So without the intervention of the IETF, we would have, or as in management, whatever that IETF came up with, we would have run out of IP addresses by now. So they came up with these 3 classes. Their vision here was a class A will give you the highest number of hosts, yeah? Is the biggest network. So when a mega corporation comes to IETF, and here they have an agency called IANA, Internet Assigned Numbers Authority. So when a company wants to connect to the internet, of course, they need an IP address. That's the PO box, right? So this would be like the poster. You go to poster to get your postal box number, yeah? So when you go there, if you're a big corporation, you get a class A. A medium-sized corporation, they get a class B. Of course, after justifying to them why you need that, yeah? And a small organization would get a class C. But these were initial interventions. You see, when networking, or when the US government invented, or US basically, yeah, invented internet, they did not envision it to have such a rampant growth. So by the early 1990s, these are actually interventions of early 1990s. So by the mid 1990s, 95, 96 time frame there, and I think it's actually earlier, right? Anyway, I don't know the time frames. They realized that this classful addressing, this is what we call classful addressing, is not managing the depletion of IP version 4 addresses well, yeah? So they came up with what we call classless interdomain routing. meaning that they tailor your IP address need based on what you need, not on this 3 scale thing of large, medium, and small organization. Yeah. So now an organization can just go to the internet gods and say, just give me a /28, as in give me a few IP addresses that I can use on my network. So they just sell you a block of that. And as a side note, to acquire a whole class A, it will cost you a lot of money, because this will give you the most IP addresses. Yeah. To get a class B, it would be slightly, this would be the cheapest of them all. But now when they went to CIDR, you can even acquire a single IP address. And many organizations use that, as in they have just a single IP address. Then they use something called NAT. But anyway, these are technologies that we'll explore later. So for now, we have seen those classes, and we know them by looking at the first octet of an IP address. Yeah. So go to your computer right now. When you do IP config, right now I'm not connected to the internet. So if I go to the command prompt of my computer and do IP config, and see that I don't have internet here. But in your case, you'll see IP addresses. So just looking at the first octet, so like here in Bara, say if you're in networking lab, you might see something like 192.168.6.0. So looking at this first octet, it will tell you whether it's a class A, B, or C. Yeah, you can see right away here, there's a class C, because class C starts with 192 all the way to 223. So if you do IP config, then you see something like 10.5.5.0. That's a class A, because this first octet falls under 1 to 126. Yeah, so for a class B, I think you get that drill. And the reason for that, these are not just arbitrary numbers. You see, the IETF, through their RFCs, RFCs is like standardization documents. It's like the Kenya Gazette, yeah, where you say this is the rule that will govern this. So they said that, so this is what I'm talking about, IENA and ICANN. These are the two bodies that manages IP addresses, yeah. So they said that the first octet, yeah, the first octet here, that now when you look at it in binary, the first bit have to always be 0, yeah. So this one you cannot, as in, have to always be off. So if you turn everything else off, that's how you get a 0, because 8 zeros, if you convert them to decimal, is a 0. So now if you turn everything else on, because this one you cannot change it, the rule have said that have to always be 0. So if you turn on all the rest, that's how you get 127. You can go to the calculator, do 0, then you have 7 ones, convert, and you'll see 127. But the usable IP address is the reason why I have this one here, and it might confuse you a bit. So officially, a class A is from 0 to 127. But we can't use 0. You can't have an IP address that you can assign to a machine that is a 0 like that. And 127 is taken. Yeah, it's taken for what we call loopback IP address. What I mean by that is, or what this loopback IP is when you're troubleshooting, by the book way of how you troubleshoot, or how Cisco recommends you do it, is so let's say you have a reception, you are the network admin of Baraton, and let's say the reception computer here, the receptionist computer here cannot access internet, yeah. So That's why you've been called, they are not able to work and all that. So how do you troubleshoot why this computer is not connecting to the internet? Yeah. So Cisco recommends that you begin by first pinging 127.0.0.1. That will always give you replies. Yeah, you can see that I'm not connected to the internet. I don't have a cable. My Wi-Fi is not connected. Everything is disconnected. Yet when I ping that, it works. The reason why they say you start from there is this loopback testing is essentially tests the TCP/IP protocol stack, whether is up and running on your machine, or essentially, does this machine understand the OSI model? Because I said the OSI model is the constitution that governs how communication happens on our network. So if I have viruses and they have corrupted my Windows, somehow, it's not understanding the OSI model, that computer cannot communicate on the network. So 127 then is reserved for that purpose to test the OSI model. So the next step in your troubleshooting, they tell you to ping your own IP address. Now, I don't have an IP address here because I'm not connected. Now, if you get replies from that, it means that the connection between you and the switch, or layer 2, you see now how we talk in the language of the OSI model, yeah? Layer 2 connectivity is sound if you get replies from that. Now, the next step is you ping your default gateway to see whether this receptionist computer can reach the default gateway, the router, your first router, to reach the, to go to the internet. If you can reach that one, then maybe the next thing that you can do, or by the book way of troubleshooting, is you do a traceat. Yeah. So maybe now you can do 8.8.8.8 to see where you're having issues, because if that computer can reach the default gateway, it can reach the router, so it means that the problem is not layer 2 all the way to the router. So all that. Anyway, I think I have way digressed. So those are the rules. For a class B, the same gods say that the first bit in the first octet have to always be set, and the second one have to always be off. So if you turn everything off, that's how you have 1000, and if you convert this number to decimal, that's how you get 128. So now, actually, by turning off, we are trying to find the lowest number that you can get. Yeah, to get the highest number is this first bit have to always be set, this have to always be off. So if you turn on everything else, the highest number that you can get is 191. So that's how a class B is 128 to 191. For a class C, the rule says that the first 3 bits, the first 2 have to always be on, but the third one have to always be off. So if you turn everything else off, that's how you get 192. So, and the highest is these 2 have to always be on and this off. So the highest you get is that one. And that's how you get 223. So here I have listed class A, B, C, and that's what is popularly used in our networks. As in, you'll walk into any machine, do an IP config, you'll most likely get an IP address from these 3 classes. But we have others, that is D and E. D is mainly what we call multicast. Yeah, multicast is usually used in routing protocols, so we'll see it from CCNA 2 and 3 when we look at how we do routing. So when you talk about routing protocols like OSPF, EIGRP, all that. So if you continue with this logic, I've not listed them here, but you can be able to tell the ranges, because like for class D, the first 3 bits have to be set, but the fourth have to be off. So if you continue with that logic, I believe you can get the range. And you can actually see why we are running out of these addresses, because we have reserved quite a lot of addresses that are not used here. And this is where I'm talking about this. And there's also this range, 169.254.anything. This one is what at times we call a PIPA, automatic address assignment or something. So this one is where if we had a switch, let's say a couple of us, we want to form a peer-to-peer network, because maybe, you know, a couple of friends, we have hooked up, we are at somebody's place with our laptop. If we have a switch, you know, we can form a small network, right? To do some sort of what they say, like a home group computer, right? A home group network, or a peer-to-peer network, where from there maybe we want to play a game. We want to play a computer game where we are competing. We have a small network here. Now, without a DHCP server, our computers might automatically assign themselves these IP addresses. The cool thing about this is these guys that want to play computers, maybe they are programmers, they know nothing about IP addresses and all. The computers can just auto-assign themselves. Basically, they can be able to work in that home group. But on this slide, I want us to think about public versus private addresses, as in, so these internet gods, still in a bid to manage these IP addresses, they came up with this rule that we have public IP addresses and private addresses. So public addresses are usable over the internet. So if you go to the command prompt right now and you ping Facebook, in my case I won't be able to, or if I ping 8.8.8.8 or whatever IP address that is not in these ranges, anyway, I was trying to say that if you ping, say, the Facebook page, you'll see that it's a public IP address. So without a public IP address, you cannot access it over the internet. So private IP addresses, I think you have seen on this slide, they are usable only on internal networks. And so in every class, we said that for a class A, the range is 0 to 127. So these guys just went for, you can see that 10.0.0.0 is in this range. So for class A, they reserved that 10 block to be used as private addresses. So for a class B, we said is from 128 up to 191. So you can see 172 is part of this range. So 172.16, they reserved it as private. And you can see why if you go to the computer that you are with right now, if you are in Baraton, if you do ipconfig, you'll see it with an IP address of 192.168. Class C is one of the most popularly used ranges, but the point here is those are private IP addresses. So one might ask, if something that have a private IP address cannot communicate over the network, how then are you able to access internet? Because remember the way the communication happened, and this is where we were explaining about encapsulation or the enveloping. So you're here connecting to Facebook. So this is meant to be a server. That's horrible. So this is Facebook that you are accessing right now. So it has a public IP address. It have to have a public IP address. Otherwise, you wouldn't be able to access it. So you see, when the packets, the envelope is coming from you going to Facebook, Facebook at some point have to respond to that letter. Yeah. And I'm using the letter term here analogously. So technically we know is IP packets will come back. So when they're coming back, when they were going this way, let's say Facebook IP address is 8.8.8.8, yeah? Let's say. So when my computer was creating that envelope, it had that IP packet. In this case, it would be HTTP because you're using your browser. Source port number, destination port number, source IP address, which is the private IP address of my machine. Then you have destination IP address, which is the IP address of that guy. So this is the destination, this is the source. When this packet, when the server is responding, the destination will be private, right, of my laptop, for me to be able to access that. So one might wonder, how then am I getting the packets if the destination, you see the destination, all the routers in that web, in that cloud, the internet, yeah, all they're interested in is what is in the destination, in the header, in the IP header. It just looks for destination address so that it can be able to route that packet. So you see, when it is reversing, if it is private, how then am I able to receive it? Yet we have said private IP addresses cannot be routed over the internet. Well, in that case, you would be wrong, or I would be wrong, because here I'm having a monologue. But anyway, so what happens is, in reality, your computer doesn't send those packets to the internet using private IP address. So we know that your computer here is connected to a switch, right, in the LAN infrastructure. A switch, we draw it as this icon with those whatever. So it will eventually hit the router, and it's the router that is actually connecting you to the internet. So we have sort of zoomed into that cloud to see the first router. So your first router is the one that will have been assigned a public IP address right on this interface here. Yeah. So when my computer now sends packets with private IP address, when they hit that router, they'll be NATed. Stands for Network Address Translation. Basically what that is, it will come with a private IP address, and this is where the source and destination port numbers that we looked at in the transport layer will come to haunt you. So they are NATed, meaning if you're to use Wireshark and sniff those packets when they're on the wire here, you'll see them with a private IP address. But when they are leaving Baraton, now going to the internet, they'll have public as the source. They'll all seem to come from one IP address. So essentially your router sort of becomes a multiplexer, and those without, those who, so a multiplexer basically is just something that accepts many, is a logic circuit, or we can say some logic gates, yeah, that will accept many inputs but one output. So in the LAN we have so many other computers, if I can draw them. They all come with different IP addresses, but they all live with one IP address. That's the power of NATing. So, and the whole logic behind that is the internet gods. What they wanted was, I can select something here. So what they wanted is, you see, that helps in proper management of the depletion of IP version 4 addresses. And the reason for that is, you see, we can say if this is Baraton's network, that's small cloud. Of course, inside there, we represent networks as clouds, right? So let's say that these clouds that I'm drawing, let's say this is Baraton University, this is Moi University, this is Nairobi University, and this is my home network. Yeah, so we'll all be connected maybe to our different ISPs, but is all part of the internet. You know, internet stands for network of networks. Basically, it means is all these disparate networks that have joined together, and that's how internet is. So we might be connected to different ISPs, but all the ISPs are interconnected and they form this one big cloud, the internet. So we all have our links, sometimes one, and by one I mean wide area network connections. We represent them as this lightning bolt that is coming from the cloud. Yeah. So here at Baraton, we can use 192.168.1.0. More, you can use the same 192.168.1.0. This other guy can use the same 16, as in we all. In fact, 192.168 is the most common that you'll find in many networks. You see, in a network, you cannot have duplicate IP addresses. Yeah, as in there's no way you can have duplicate IP addresses and then you have communication. So what makes all these guys unique is the single public IP address that will have been assigned to Baraton, and that was assigned to Moi, and all that. So when all the traffic that is leaving Baraton is going that way, it is hidden. Yeah. So you see there you're able to reserve or to manage the depletion of public IP addresses, because you see here you're just using one, or what I'm trying to say is here we have just used 4 public, so you have 1, 2, 3, 4. Yeah, to address all these networks we have used just 4 public IP addresses. Without this concept of private IP addresses and NATing, it means that all the computers in Baraton, let's say Baraton have 50, and not 50, of course, is let's say Baraton have 600 computers. Yeah, if you walk around, you have 600, and of course the number is far much higher than that, because you have people with their phones, with their smartphone. You connect to Wi-Fi. Of course, this would be over 1,000 connected devices. You have printers in there. Yeah, every gadget, every networked gadget in Baraton. Without this concept, it means that would have taken 1,000 public IP addresses. Now, if you're taking 1,000, they take 2,000. Big corporations will even take a lot more thousands like that. So you can see that our 4.7 billion addresses will have run out by now. So this whole thing is all in a bid to manage those addresses. Now, looking at the time, I see that this have taken way longer than what I wanted to cover in this video. So I'll split this video into 2. So in part 2, that's where now we will delve into TCP IP subnetting. So for now, I hope this has been informative to you, and I'd like to thank you for viewing.